We are going to talk about logarithmic differentiation. So this is kind of a complicated way of saying we're going to use properties of logarithms to make computing derivatives easier and be able to compute some derivatives that we would not be able to compute otherwise. So first, as a reminder about the laws of logarithms, sometimes these are also called the log properties. So if x and y are positive numbers, then the following is true. Log base b of x times y equals log base b of x plus log base b of y. Second, log base b of x divided by y equals log base b of x minus log base b of y. And third, log base b of x to the r equals r log base b of x for any real number r. And so these are our properties of logarithms. And so now the idea of logarithmic differentiation is we're going to use these properties to kind of simplify derivatives and then take an implicit derivative rather than taking a more complicated derivative. And so as a motivating example for what we're doing here, we want to differentiate y equals x to the 3/4 times the square root of x squared plus 1 divided by 3x plus 2 to the 5th power. Now I want to make this clear. We know how to take the derivative of this already without logarithmic differentiation. Basically, this would be a product rule with chain rules and a quotient rule. So it'd be a very complicated derivative. What we're going to do is we're going to take the logarithm of both sides, specifically the natural logarithm because it has the nicest derivative, and then use log properties to simplify the derivative we're computing. And so we're going to take ln of both sides. So we've got ln of y equals ln of x to the 3/4 square root of x squared plus 1 divided by 3x plus 2 to the 5th. And so now the left-hand side is just log of y, which we can compute the derivative very easily. But we can simplify the right-hand side using log properties. So notice this is a division. So we're going to have ln of x to the 3/4, the square root of x squared plus 1, minus ln of 3x plus 2 to the 5th. But we've now got a multiplication in the first term. So this is ln of x to the 3/4 plus ln of the square root of x squared plus 1 minus ln of 3x plus 2. But now we've also got these exponents we can pull out. So this is 3/4 ln of x plus 1/2 ln of x squared plus 1 minus 5 ln of 3x plus 2. And so using a bunch of log properties, what we were able to find then is that we've got ln of y equals 3/4 ln of x plus 1/2 ln of x squared plus 1 minus 5 ln of 3x plus 2. And now we're going to take an implicit derivative of both sides. So we're going to take the derivative with respect to x because we want dy over dx. And so on the left-hand side, we're just taking the derivative of ln of y. And so this will be 1 over y dy over dx. And now we take the derivative of the left-hand side, or the right-hand side, I mean. So we've got 3/4 ln of x plus 1/2 ln of x squared plus 1 minus 5 ln of 3x plus 2. And so we have 3/4 times the derivative of ln of x, which is just 1 over x, plus 1/2 times the derivative of ln of x squared, which is 1 over x squared plus 1, times the derivative of x squared plus 1, minus 5, times the derivative of ln of 3x plus 2, which is 1 over 3x plus 2, times the derivative of 3x plus 2. Now, computing these, we get 3 over 4x plus 1/2 times 1 over x squared plus 1 times 2x, because that's the derivative of x squared plus 1, minus 5 times 1 over 3x plus 2 times the derivative of 3x plus 2, which is just 3. So this becomes 3 over 4x plus, we have a 2 here, which cancels with the 2 there, so we just get x over x squared plus 1 minus 15 over 3x plus 2. And so that's then what we compute for the derivative of that side. And so now this equals, we set the two sides equal, so we're going to get 1 over y, dy over dx, equals 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. Multiplying by y on both sides to get dy over dx by itself, we have dy over dx equals y times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. But we know what y is. Remember, y was just our original expression. So y is this really complicated looking expression that we had before. And so what we're going to do is we're just going to plug that back in. So we get dy over dx equals y. And remember that y is equal to x to the 3/4 square root of x squared plus 1 divided by 3x plus 2 to the 5th. So that's y times this expression that we have, 3 over 4x plus x over x squared plus 1 minus 15 over x plus 3x plus 2. And so that is our derivative. And so rather than having to use a bunch of product rules and quotient rules, we ended up just making it into a number of chain rules, which ultimately created an easier derivative for us to compute. So now that we've done an example, let's actually list the steps of logarithmic differentiation. So the steps to logarithmic differentiation. So step 1 is take the natural log of both sides. So we just take the natural log of both sides. Step 2 is use log properties to expand the side involving x. Step 3, differentiate implicitly with respect to x. Step 4, solve for dy over dx. And step 5, replace y with what it equals. Which normally that'll just be the original function. So you're just replacing the original y with the original function. And so this, as we saw, allowed us to take what would have been a fairly complicated derivative and make it into a somewhat easier derivative. And so let's look at another example of actually doing that process. So we want to take the derivative with respect to x of the square root of x minus 1 divided by x to the 4th plus 1. So we're going to take this derivative. So rather than actually computing this derivative, which we do know how to do with the chain rule and quotient rule, we're going to set y equals to the square root of x minus 1 over x to the fourth plus 1. And we're going to do an implicit derivative. So we're going to take a log derivative, So we're going to take natural log of both sides. Now everything's square rooted, so we can pull a 1/2 out of the logarithm to get 1/2 log of x minus 1 over x to the fourth plus 1, which is 1/2 times ln of x minus 1 minus ln of x to the fourth plus 1. Just breaking up over subtraction, because out over division, which becomes subtraction. So now we take the derivative implicitly of both sides. So the derivative of ln of y is 1 over y dy over dx. Now, just as a note, that'll always show up when you do logarithmic differentiation. So that part is the same every time. Now we do the other side. So we have the derivative of 1/2 ln of x minus 1 minus ln of x to the fourth plus 1. So this is going to be 1/2 times the derivative of ln of x minus 1. It's going to be 1 over x minus 1 times the derivative of x minus 1 minus 1 over x to the fourth plus 1 times the derivative of x to the fourth plus 1. So again, we're just using the chain rule there. So this becomes 1/2 times, we're going to have 1 over x times the derivative of 1 over x, but the derivative of 1 over x is just 1. And then we have minus 1 over x to the fourth plus 1 times the derivative of x to the fourth plus 1, which is 4x cubed. So this is 1/2 times 1 over x minus 1 minus 4x cubed over x to the fourth plus 1. So that then is our derivative of the right-hand side. And so now we are going to set these equal to each other. And so setting them equal, we get 1 over y dy over dx equals 1/2 times 1 over x minus 1 minus 4x cubed divided by x to the fourth plus 1. So dy over dx then equals y over 2 times 1 over x minus 1 minus 4x cubed divided by x to the fourth plus 1. And now we are going to plug back in what y is equal to. And so we know what y is equal to. And so this then becomes y, which is the square root of x minus 1 over x to the fourth plus 1, times 1/2 times 1 over x minus 1 minus 4x cubed divided by x to the fourth plus 1. Now, I'm going to multiply the 1/2 in just to make this look a little bit nicer. So this is the square root of x minus 1 over x to the fourth plus 1 times, I'm multiplying the 1/2 in by distributing, so we get 1 over 2x minus 2 minus 2x cubed over x to the fourth plus 1. And so that then is our derivative, just using logarithmic differentiation on this expression that we had. And so while we could have taken the derivative using techniques that we already knew, we were able to make it a bit easier using logarithmic differentiation. So logarithmic differentiation actually lets us compute derivatives that we otherwise would not be able to compute. And so we're going to do another example, and this time we actually wouldn't be able to do it without logarithmic differentiation. And so what we want to do is we want to differentiate y equals x to the square root of x. So we want to compute this derivative. And now the reason why we couldn't do this beforehand is this is not a power function and not an exponential function. And it's not a composition of those either, because we have x both in the base and in the exponent. And so we are going to use logarithmic differentiation to kind of fix that problem. So we're going to take the natural log of both sides to get ln of y equals ln of x to the square root of x. Now we can pull exponents down, so this becomes the square root of x times ln of x. And so we now have this. So now we're just going to take derivatives implicitly. So we have the derivative with respect to x of ln of y, which is 1 over y dy over dx. And the derivative of square root of x ln of x. This is a product rule, so we take the derivative of the first thing times the second thing, plus the first thing times the derivative of the second thing. The derivative of the square root of x is 1 over 2 square roots of x. We multiply that by ln of x, plus the square root of x times the derivative of ln of x is 1 over x. So this becomes ln of x divided by 2 square roots of x, plus we've got the square root of x times 1 over x. That's just going to be 1 over the square root of x. And so this then becomes ln of x plus 2 divided by 2 square roots of x, just getting a common denominator of 2 square roots of x. So I just multiplied the second one on the top and the bottom by 2. And so now we set the two sides equal. So we have 1 over y dy over dx is equal to ln of x plus 2 divided by 2 square roots of x. So dy over dx equals y times ln of x plus 2 divided by 2 square roots of x. But we know what y equals. Y is x to the square root of x. So this becomes x to the square root of x times ln of x plus 2 divided by 2 square roots of x. And so that is our derivative. So in other words, the derivative of x to the square root of x is just x to the square root of x times ln of x plus 2 over 2 square roots of x. And we would not have been able to compute that derivative without knowing logarithmic differentiation. So we're going to do one more example that's very similar, just to kind of reiterate the point. So we're going to compute the derivative now for f of x equals sine of x raised to the x. So we're going to compute the derivative of sine of x raised to the x. And so what we're going to do is set y equal to sine of x raised to the x. Then ln of y equals ln of sine of x raised to the x. We can bring the x out in front using log properties to get x ln of sine of x. And now we're going to do an implicit derivative. So we're going to take the derivative with respect to x of ln of y. So this is 1 over y dy over dx for the left-hand side. And then the right-hand side, we're taking the derivative of x ln of sine of x. So the derivative of x times ln. So now computing this derivative, we're going to have the derivative of the first thing times the second thing plus the first thing times the derivative of ln of sine of x. The derivative of x is just 1, so we're going to get just ln of sine of x plus x times the derivative of ln of sine of x, which is 1 over the integral function, so 1 over sine of x, times the derivative of sine of x. So we get ln of sine of x plus x times, we're just going to get cosine of x over sine of x. So this is ln of sine of x plus x cotangent of x, because cosine over sine is cotangent. So setting the sides equal, we have 1 over y, dy over dx is equal to ln of sine of x plus x cotangent of x. Then dy over dx is then y times ln of sine of x plus x cotangent of x. But y was sine of x to the x. So this is sine of x to the x times ln of sine of x plus x cotangent of x. And so that is then the derivative of sine of x to the x. And so we were able to compute a derivative that we otherwise would not have been able to compute using logarithmic differentiation.